Hello and welcome to Easy Projects. So this will be part 3 of the DIY power supply, and in the last video we tested each of the two components separately, so the voltage control and the current control. And in this video I want to build it all into one circuit and test that it actually works together. However, there is one silly mistake that we need to fix first. I don't know if any of you picked it up, but you can have a second and pause the video if you want to have a look. I should have noticed it earlier. So we can control the voltage with this section and the current with this section. So if we set a voltage at 1 volt, say, and we have a load of a few kilo ohms, let's say we're powering a microcontroller or something. We have just turned the current control all the way up, because we don't really care about current limit. Well, then this op amp will be fully on. There's a resistor in the path, and then we have the transistor, which is basically the base emitter. Junction is basically just a diode. So we just supply 30 volts through here and to the microcontroller, which would then burn out. Not the best idea in the world, so I don't know why I didn't think about that in the previous video, but I should have. So the way to fix it, if we still want to use two transistors, could be to take the voltage regulator and put it after the current regulator. That way it will be the current regulation that is not 100% good down at the lower end, but at least if we turn the voltage down, it will go to 0. So I just drew a simplified version of the new schematic here with the two parts flipped. So we now have the voltage controller here and the current controller here. We still have a problem where if we set a high voltage here, let's say 10 volts, and then we turn the current down to 0 milliamps, then this op amp can still push current through the transistor and deliver some current even though this section is completely off. So what we need to do is increase the size of this resistor until the current doesn't really matter if it's less than a milliamp or something. But we can't do that since we also need to be able to drive this transistor hard when we need a high current to the load. We can do something a little bit similar to increasing the resistor value, but we will need to include a second transistor. So let me just draw that. So if we add the transistor here, we can have a low value resistor here that will allow us to push a lot of current, and we can have a high value resistor here that when this is off only allows a very tiny amount of current to go out through here. We already have a way to turn off this voltage because we can just connect it over at that point. So when the current exceeds our set limit here, this part of the circuit will turn off. It will cut the power to this transistor, but the op amp will still be able to push a little bit of current out through here. So this circuit is still not what I want, and we will have to change it later, but in this configuration at least we can test the setup that I already put into the breadboard. So let's go ahead and do that. Then afterwards we will take a look at how we fix it for good. So here is the updated mess, and we have the two transistors now. This one controls the current and this one controls the voltage. I have a potentiometer for each, for the voltage and for the current. And then I put a load resistor of 10 ohms. So we should see 1/10 of the current, of which we have voltage. Right now it's set to just over 1.5 volts. So you can see that both on the scope and on the multimeter. So the first test of any power supply is to see if it goes down to 0 volts, which it should. And we have a dead 0 there, so that's fine. So now let's try and set it to 5 volts. Or maybe let's just sweep the entire voltage range and see if we get any oscillations on the scope. Nope, it doesn't look like it. So we have 5 volts there, and we are drawing exactly 500 milliamps on the power supply. So now let me turn down the current. So it looks like the voltage is drifting a little bit when the transistor heats up and cools down. This could also be a problem with the ground, since I'm using a diode to drop the voltage to the op-amp. Yeah, so that was because of the diode. Now I changed it, and it's stable now, but of course it doesn't go down to all the way down to 0 volts now. But in the final design we will have a designated voltage rail for the negative voltage to the op-amp, so we won't see this problem, of course. So we're back at 5 volts, and now let's see if we can adjust the current. So also I had to add the diode again to get the current limit to work, as I mentioned in the previous video. So let's see if we can regulate the current from almost 0 to 500 milliamps. But again, when I turn this down, it should go to 0, but it doesn't because of the current flowing in through this resistor here. Something we need to fix, of course. So let's turn the voltage to the maximum and see if we can adjust the current. So it looks to be pretty stable here with a 10 ohm resistor. Let's change the resistor to 1 ohm, and then we can test it all the way up to 3 amps. So I changed it to the 1 ohm resistor, and now 1 volt per division instead of 4. So 3 volts should equal 3 amps. Let's see how it does. So we're starting to do something. Yeah, it actually looks more stable than the previous version. I also tried to do a little bit better grounding, even though I still have the long wires, but looks like we can get it to work. We just need to make it go all the way down to 0 milliamps as well. So I've just set 1.3 amps, and you can see we're at 25 volts on the input, and we should be on 1.3 volts on the output, so we're dropping roughly 23.7 volts at 1.3 amps, so that should be right around 30 watts or something like that. So the transistor itself is getting fairly warm. I couldn't stay with my finger on there all day, but the heatsink is still around 40 degrees or so. But it will heat up, of course, so I never really expected to run at an amp without the fan going, of course, in the final design. As long as I can get a few hundred milliamps out of it without having the fan noise, that would be fine. So with the 2 transistor design here, we would expect the current regulator to do all the regulation. So this gets fairly warm. It's definitely regulating, and we would expect this one to be almost cold, which it is. It is lukewarm, but it might be from the voltage test. There's still some heat in it. Now we should be able to turn the voltage down like that, so to just below the 1.3 amps. So now the voltage regulator should be doing all the regulation, and this should cool down again. And this one is indeed getting hot now. So let's see if we can solve that problem where we couldn't turn the current all the way down, and maybe throw away one of the expensive power transistors in the process. So if we look at the top part of the circuit, it is just a voltage regulating circuit from the previous schematic, and I added in the current sense resistor here. But we take the feedback after the resistor so we don't get a drop in voltage. Then down here I drew the current regulating circuit without the transistor. So we have the current sense amplifier and we have the op amp, and we can set it here. Note that I switched the inputs and it will become clear why. If we want to throw away one of these transistors and just have one, we need to do something to this path here to limit the current. Of course, if we can drag this voltage low after the resistor here, then the current from this op amp will just go to ground, and leaving no current to go to the output. So if we do something like this, it should work. So if we again ignore this part of the circuit, it's just a voltage regulator, and then we measure the voltage drop across this resistor, which indicates the current. We feed it into the current sense amplifier and into the non-inverting input of this op amp, and we feed the set voltage into the inverting input. So as long as this is lower than the set point, this op amp will be completely off, this transistor will be completely off, and you can basically cut this wire. So it'll just be a voltage regulator. On the other hand, when this current increases the set point, the op amp will turn on. It will turn this transistor on. Let's just say it turns it fully on. Then it will drag this voltage all the way down to zero, almost, or at least below the base emitter forward voltage of this transistor. So it will turn this transistor completely off, leaving 0 milliamps to go to the load. And if this transistor is off, so will this one be, and there's nothing that can deliver any current. So now the only thing that can prevent us from going all the way down to 0 milliamps on the output when we turn it all the way down is errors in the current sense amplifier or in this op amp. So if the op amp has an input offset voltage, that might create a little bit of voltage on the output, even though it should be 0. And likewise for the current sense amplifier. But if we pick good enough components here, we should be able to get at least below a milliamp or 100 microamps, which should be fine for what I need. So let's try to build this circuit and test it and see if it is any better than the previous one. So I built up the new circuit here. As you can see, one of the transistors are gone, and now instead of this transistor controlling that transistor that we removed, it will now pull this transistor low. And I also flipped the inputs of the op amp to control this one, just as I showed on the schematic. So now let's see if it works. So you can't see that. Now you can. So you see the output voltage on the multimeter here, and also on the scope. So the first test again, see if it can go down to 0. Good enough. And let's see if it will go all the way up to 3 amps. Yep. And we have no oscillation, so that's fine. Let's, oops, too much. Let's put the current at 3 amps again and turn down the current knob. Now it oscillates, and it doesn't even regulate. Oh, maybe it does, but it oscillates like crazy. No, it doesn't. It jumps from 700 milliamps and all the way up to 3 amps. So So what we have here is basically these two transistors fighting for which one should control the transistor. And if there's some capacitance somewhere in the loop, it will start to oscillate. So what we can do is try to lower the impedance of one of the transistors. Not entirely sure which one, but we can try. So I tried the voltage regulating transistor first, and that was interesting. And now I moved it to the current side, and now have a look at this. Let me turn, oh, I'm turning the wrong part. So see, this basically made it a lot worse, which tells us that we're probably doing something wrong. So let's move it to the other transistor. And now let's try again. Oh, see, so far, so good. So you could argue that it is a little bit unstable, but it has always been that due to that diode that I'm using to drop the voltage on the op amp. So I believe we can fix this issue when we get a proper negative rail. And as you can see here, when I turn down the current, we go straight to 0 volts on the output, and of course that would mean we have 0 milliamps as well. So the capacitor we added is this one here, between the output of the op amp and the base of this transistor, so basically shorting out this resistor at high frequencies. So we can take a quick look at what it does, but I'm not going to go into details about how to calculate the values and where to put them and all that in this video. It is a bit complicated topic, and I'm no expert in that in any stretch of the imagination, but if we remove this part of the circuit for a while and just focus on the voltage regulating circuit. And I just made a simpler circuit here to look at. If we say we set a sine wave on the input instead of a DC voltage, then it will look something like this. And if we say we have a ×2 gain in the loop here, we would expect something like this on the output. The op amp will compare what's on the two inputs here, and it will do whatever to the output to make sure that the inverting input reaches the same level as the non-inverting input. So you can imagine if somewhere in this path here we have some delay. Let's just add a delay. Let's not focus too much on what this is right now. Then you can see that our non-inverting input still sees the original waveform here, and the waveform that comes back through the loop here will be delayed a little bit. Say something like this. So this is not drawn very well. It should have lined up with the other waveform, just delayed a little bit. But you can see at this point the top waveform has been delayed 180 degrees compared to the bottom waveform. So now when the op amp compares these two, it will say, oh, we need to bring this way down because it's much above this waveform. So it'll try to bring this down, but remember the delay or phase shift in the loop here makes this point into this point down here. So it will actually make this one go further down, which would in turn make this one go further up. And this will make a perfect oscillator. So of course we're not using sine waves in the power supply, we're using a DC voltage. But you will always have some noise on top of that DC, and if some of that noise gets delayed enough, it will start to amplify and it will turn into oscillations, which we saw. So if we just take a look at one example that could cause this, say for some other reason we have some capacitance right here, which we don't want. So this will form an RC circuit, meaning that if we raise the output voltage of the op amp, it will take a little bit of time before it reaches that level on the capacitor here. If we can maintain a perfect DC voltage through the system, it shouldn't matter because the capacitor is basically not there. at DC, but there will always be the noise, and when you turn on and off a load it will make some transients. This will also reduce the high frequency response of the system, because any high frequencies going up through here will just be eaten up by this capacitor. So what we can do is to add another capacitor between the output of the op amp and the transistor to basically cancel out this resistor when we go up in frequency. So the same frequencies that would be pulled to ground by this capacitor will also get straight around the resistor here, not being attenuated. So you have a lot more power in that as part of the spectrum, which will make sure that not all of it at least goes to ground. Of course, if you have a more complicated circuit, you might have more elements that cause delay. There will always be some capacitance on the inputs of the op amp, just in the traces and in other components. So you might need more of these capacitors. Usually they are very small in value, but since I'm doing it in a breadboard, I use fairly large values because the wires has inductance and there's capacitance in the breadboard. So usually it's in the picofarads, maybe up to a few nanofarads, that you put in these compensation capacitors. But in case of a breadboard, just by doing this, you can change the inductance and capacitance by those amounts just by touching the wires. So you need a bit more in a breadboard. You can also just take the entire loop into consideration by putting a capacitor directly across here. So what you would do depends on the application, and you could do a combination of many things. And again, I won't claim to be an expert at this, so you might want to look it up on the internet if you want to know more about it. You can of course calculate these things if you know the capacitance and inductances and all that, but if I start doing math here, 95% of you will be gone within 2 minutes, so let's not go there. So I think in the next video we will take a look at the components we're going to need. Apart from the transformer, we will have some kind of bridge rectifier. We will have some big capacitors. We will need to pick a power transistor, some other transistors, and the op amp. We will need some regulation for the op amp. So we need a positive and a negative power rail. We will figure out how to generate the negative power rail. And we will need the current sense amplifier as well. I'll have to use a different one so that I can lower the value of the current sense resistor, because this is getting too warm, and since the resistance increases with temperature, the current sense will drift when you draw a high amount of current, and I don't want that. And we'll also have to pick the current sense resistor and other things as well. We'll need the ADC and the DAC so we can get rid of the potentiometers, and so that we have a way of reading out the current and the voltage. So when I get all the components here, I'll have to make a PCB, and I'll also have to make the software for the microcontroller, which I think will be the Arduino DUI, because that's what most people are familiar with. And after we have made the PCB and we get a working unit, we will have to test it and see that it's within specification, first of all, that it doesn't oscillate or have any strange behavior, and we'll need to characterize the output and the transient response and all of that stuff. There's no point in doing that now really, because we have all the long wires and the breadboard, and it will change totally once we put it onto a PCB anyway. So we can just confirm that it kind of works now, and then we'll put it on a PCB and we'll do the tests, and we will do any modifications to the PCB. So I think that's it for this video. Thank you very much for watching, and if you liked it, please give it a thumbs up, and I hope to see you in the next one. See ya!